So we're going to continue where we left off in the previous presentation. I ran out of time. I try to limit these to a half an hour. So we're going to continue where we left off in the previous presentation and start talking about virtualizing of networks in the data center. And basically, when we talk about network virtualization, if you think about it, all of these virtual machines are running as software and there's no physical interconnection. So let's say you had a virtual environment running 1,000 VMs. All of those machines never connect to each other through any physical network infrastructure. It's all virtual, right? They're all connecting virtually. So we have to approximate the same functionality that we have in a physical network, we have to approximate in the virtual network. So we have tools to do that. And in theory, we can virtualize much of even our physical networks through virtualization. So network functions virtualization, or NFV, is this concept that we can take the functionality that we find in network adapters, switches, routers, and load balancers, and we can use those in a virtual environment, or we can virtualize that functionality. And very often, NFV also has security enhancements, which we'll talk about security in the last part of this unit. But sometimes they have security enhancements such as firewalls, and they have baked in intrusion detection and prevention systems like IDS and IPS, as well as antivirus management. And hopefully you've learned about some of that stuff in your other classes. Sorry about the typo in this slide. Dave Center should be Data Center, not Dave Center. But some data center virtualization products provide for teaming of network interface cards to increase the speed and fault tolerance of your network interfaces. So you have this one huge host hosting many virtual machines. All of a sudden, fault tolerance and performance for the network interface card becomes really important because you're sharing that network interface card amongst many virtual machines. So using teaming, so basically what teaming does is it allows you to take multiple network interfaces and they can work together as a team. So they all kind of run concurrently and allows you to have to use and aggregate the bandwidth available across those different NICs, and also gives you fault tolerance in the event of a failure of one of those NICs for some reason. And in many cases, people will interconnect those team NICs through different switches and things like that to even further provide for that fault tolerance. Okay, so moving along. So as far as virtual network adapters, the virtual network adapter, the hypervisor, emulates a network interface card's functions and provides the guest operating system with a software driver for the virtualized NIC. That works the same in Type 1 versus Type 2, so not much has changed there when we talk about Type 1 hypervisors in the data center. It works pretty much the same as you will see, or that you saw in the labs with the Type 2 hypervisors, and used to gain access to the outside network by being assigned to a switch that is connected to the physical NIC. So you actually have to physically connect that NIC to a physical switch. And we've learned in previous courses, hopefully you learned about MAC addresses and you understand what those are, but I don't want to waste too much time talking about MAC addresses. But basically with virtual network adapters, the idea is that the virtualization software or the hypervisor knows the MAC address of all the virtual machines for which it's responsible for. So when traffic comes into the virtual host, into the virtualization host, the hypervisor host, it when it looks at the MAC address of the frame, so when it reads the frame in the in TCP/IP, it's going to read in the frame which contains the MAC address, the source and the destination MAC address. It's going to take that destination MAC address, write the frame into memory, and then provide it to the virtual machine. So it's providing that sort of network layer as an intermediary between the physical machine and the virtual machine, which of course is the hypervisor's job, and it does that for all the different hardware that we've talked about. But it is important to kind of understand, how that sharing of that network traffic works with the hypervisor and things like the VM kernel, for example. So VMs access the physical network using the host computer's physical network adapters, which I just talked about. Both bridged and NAT switches utilize one of the host physical NICs. Using multi-port network adapters reduces the number of expansion slots needed. So a lot of these newer network cards and the motherboards, they have multiple network adapters on a single, or multiple network interfaces on a single adapter, so that you can get more network interfaces in a smaller form factor, I guess I should say. So TCP/IP really doesn't change much when we talk about virtualization. The concepts are pretty much the same. It's the same suite of protocols that we've been using since the 1980s. They pretty much work the same way. I talked a little about MAC addresses before. And there, of course, there are two versions of TCP/IP or IP really that are in use today: IPv4 and IPv6. And all of that stuff really remains the same with virtualization. Yeah, so everything that you've learned in your classes about IPv4 and IPv6, none of that really changes with virtualization. So IPv4, you have 32-bit addresses that are assigned to each computer. There's a host portion of the address and a node portion of the address. So, the two portions of the address that you learn about in subnet masking, for example, which I touched upon earlier. TCP/IP also allows for private IP addresses, and um, you can also use loopback addresses, which we talked about before. One thing that we should probably talk about just very briefly too is that with most virtual environments, it makes a lot of sense to use DHCP because it reduces management. And again, none of this is really different in virtualization as it is for physical networks. We use DHCP the same way, but it is important to know that this is definitely one of the things that we're going to use with virtualization to try to reduce the amount of management we have to do. And I'm sure they've mentioned it in other classes that with DHCP, if you're doing troubleshooting, if your virtual machine or any machine gets a DHCP address that starts with 169 dot something, there's a good chance that you have an APIPA address, which is basically means that it couldn't find a DHCP server on the network. Now, I should mention, as far as troubleshooting goes, with virtualization and virtual networks, sometimes troubleshooting can be a little bit more difficult because there's more layers, right? So with physical networks, you have the physical network interface card, which connects to a physical switch, and you can kind of trace that connection, and you can isolate more easily isolate, and it's easier to conceptualize that isolation when you're doing troubleshooting. But with virtualization, there's nothing for you to see, nothing for you to touch. It's all in software, so sometimes they can be a little bit more difficult to trace down those issues. So I did just want to mention briefly that that it is sometimes a little bit more difficult to trace down these issues. But one thing that you would look for with DHCP, and this goes for DHCP in general, is look for an APIPA address to see if it was not able to contact the DHCP server. So as far as IP addresses go, this is just a graphic that shows you the network versus the node portion of the IP address. This would be an IPv4 address that you're looking at here because it's 32 bits. Again, I think you cover this. Usually, this is covered with with a lot of detail in other courses, and I don't want to waste a lot of time. But it is something that you have to know for virtualization. It's good to understand these different classes of addresses. All these things in IT are interrelated, so we really do have to rely on some of the knowledge that we have about networking when we do virtualization. And you're going to see this in the lab. So when you look at the VMware labs for network virtualization, a lot of the steps and a lot of the activities that you do are going to require that you know a little bit about networking, that you remember some of the stuff about networking. And again, if you find yourself kind of lost in some of these networking concepts, maybe you haven't taken one of those courses yet, or maybe you're, or maybe you just don't remember this stuff. Number one, you can look at the optional networking video I have for this course, where I kind of prerequisite a lot of this stuff that you can go back and look at. And also, if you search my YouTube videos on YouTube, I've got some networking course videos that you could watch to go back and kind of refresh on some of that stuff. So I'm sure most of you are familiar with what a switch is. We also have virtual switches, which is basically the hypervisor. So the hypervisor in a virtual machine is basically has to operate as a switch. Like I said before, you might have hundreds of virtual machines on a single host, and the hypervisor has to act as the switch for those hundreds of machines because there is no physical switch for those machines, and it all interconnects through that virtual machine or through the host for that hypervisor. So it's important to understand, that we have to have this, the network virtualization has to happen because of, just inherent in this, in the virtualization technology, because we have all of these machines running on a single environment. So we have to have virtual networks. A virtual LAN is basically a VLAN. So with regular switches, you can do VLANs where you can segment the network. We can do the same thing with virtual switches in the hypervisor. You can create VLANs in the hypervisor as well, and it'll make sure that you can have groups of virtual machines that can only access each other. Now, why is this important? Because here's the thing: you may have in a virtual environment you may have lots of virtual machines running for the organization, and in the physical world, it's easy to segment different servers that are being, operated by different departments or organizational units. It's easy to segment those things in the physical world, but in the virtual world, if they're all sitting in one huge virtual machine, what's to stop them from all being able to see each other's traffic and all being able to talk directly to one another? If you want to segregate those networks, if you want to segment those networks, you want to make sure you have the tools just like you would have with a physical switch. So our virtual switches allow you to do VLANs. And I know that's a little confusing because we're using the same term to describe two slightly different things. Um, a virtual, so you can use virtual switches to create VLANs or virtual LANs within that virtual switch, just like you can on a physical switch. And that's an important feature. You can get away without VLANs in a physical network by just simply using different switches and different subnets and having them interconnect through routers. But we don't have that luxury with our virtual networks that when they're all running in the same virtual machine or same hypervisor. So the hypervisor has to be VLAN aware to know how to segment those different networks within itself. All right, so I talked about this concept of logically grouping these networks. So we sort of went over that. So software-defined networking is basically a way of managing the flow of data across complex switch network environments, which can include physical and virtual switches. So what's important here is software-defined networking allows you to extend virtual networking beyond the hypervisor. So instead of just having, so far I've been talking about these network features that are within the hypervisor, within within the virtual host or the host that's running these virtual machines, but that can extend beyond the walls or beyond the boundary of the virtualization into the physical devices. And software-defined networking is one of the things that allows that to happen. And you might be asking yourself, well, where do I get devices that are compatible with the hypervisor or all these different hypervisors that can, what if I have a data center with different hypervisors and all different network infrastructure? How does all this stuff, integrate and talk to each other? Well, OpenFlow is a standard that allows that to happen. It's a common open source protocol that allows communication between those physical devices and the hypervisor's virtualized network devices. So OpenFlow is what allows that configuration. So basically, what happens here with OpenFlow is our network basically we no longer have to make the distinction between the physical components of the network and the software components of the network. The software that's running in the hypervisor versus the physical devices that we have, sitting in a rack somewhere. Now, so I'll give you an example. Let's say you wanted to do VLANs and some of your machines are physical and some of the machines are virtual in the hypervisor. Well, the hypervisor has the ability to do VLANs within the hypervisor, and a physical switch has the ability to do VLANs. But what if I need those VLANs to cross that boundary so that the VLAN is the same for some devices on the physical switch and some devices in my virtual switch inside the hypervisor? OpenFlow allows that to happen. So OpenFlow allows these network devices to work with each other so that you can create a VLAN and have some devices that are physical. I'll give you another example of that. Let's say you have virtual machines running in the data center and you have client workstations and computers that are physical that are throughout the organization. Well, if I want to use VLANs and leverage VLANs for segmentation on my network to make sure I'm keeping networks completely separate, there's lots of good reasons to do that in network security. The only way I can do that across both the physical and the virtual environments is to have something like OpenFlow that allows these different devices to work with one another. So OpenFlow, again, is a pretty important protocol as far as interconnecting the physical network devices and our virtual network devices. And here you can see that the basic concept is that you've got the virtualization layer at the top. You've got OpenFlow compatible devices in the middle that can work with the virtualization layer. So we can have things like VLANs across both environments. And it's not just VLANs. There's lots of other technologies in networking that we can span across both the virtual and the physical realm by using standards like OpenFlow. Now, by the way, I believe Cisco is one of the big vendors that supports OpenFlow, which is, of course, is one of the largest networking vendors in the world. So if they support OpenFlow and VMware supports OpenFlow, that's going to cover a pretty large percentage of data centers if they all support that. All right, so within vSphere, and you're going to see this with the lab. So one of the labs that I assigned is to use VMware's virtual networking products to get kind of a sense of those. So vSphere does have virtual switch, which I talked about. There's standard switches available in all versions, and then distributed switches, which you can use with vCenter, which can be accessed from VMs running on any host managed by the vCenter server. So basically, you can use the standard switch is a switch available within the hypervisor on a single host running virtual machines, where distributed switches is where you can have multiple VMware hosts running virtual machines. That acts as one giant switch, so you can leverage a lot of these features across many different hosts running VMware. So to connect the virtual switch to the physical network, like I said, OpenFlow is going to be important to do that, but in order to interconnect them, you're going to have to use uplink ports on your switches and configure an uplink on the from your virtual switch. So the process of assigning multiple NICs to a virtual switch type is called teaming. We talked about teaming earlier in this presentation, but that's how you do that. So in addition to allowing traffic to be grouped by type, port groups can also allow assigning network policies. And vSphere provides for 3 types of network policies: security, traffic shaping, and NIC teaming. All right, with Hyper-V, Hyper-V offers 3 types of virtual switches: private, internal, and external. So private is basically a switch that limits communication to only VMs within the host. So what that basically means is that all the VMs that are running within a Hyper-V host can talk to each other. And then when you use the internal switch, that means that the host can also talk to the virtuals that are talking to each other over the network. And then external is what allows the virtual machines in Hyper-V to communicate with the external network, which is probably what we really want in most cases, unless you're running some kind of a test environment or something like that. For most of our production IT infrastructure, we're going to use external switches. Hyper-V's extensible switch is designed to support additional features through the addition of third-party plugins. I'm not really familiar with how this works, I hate to admit, but certainly you can probably Google and do some research on this. I think some of the reading I gave you does talk about how this works, but I'm not as familiar with Hyper-V as I am with VMware. But like I said, I think Hyper-V is starting to become a little bit more popular, so it's certainly important to take a look at that.